yesterday a student asked a question. I don't know if the student is here yet. Probably not. Oh, you're the one who asked. Yeah. If there is a big star like a red giant paired with what, white dwarf? White dwarf, and the two are going around each other. Can we expect gravitational waves? Yes, you can. I mean, any system that is non-stationary and accelerating will produce. I mean, if it is accelerating, it is non-stationary, it would produce. What it means is that there aren't any time symmetries in the system. If you have learned general relativity, what it means is that there are no time-like killing vectors that describe the system. Otherwise, you will generate gravitational waves. Put it in very, symmetry formulation. In reality, what we want is non-vanishing quadrupole moment tensor. But I want to show you with a very simple argument, which I normally use in most popular lectures and introductory lectures, that Einstein's equations already tell you that the most powerful gravitational wave sources must necessarily be compact. Compact in the sense that they accommodate more mass for their size, not volume, not density. It's not density that is important, but it is the size of the system. And that goes by the name compactness. And this compactness is a very crucial quantity in almost all calculations of gravitational waves. And for a system of size R, capital R, and mass, total mass, characteristic mass, M, this compactness, C, is defined as Gm by C square R, where G is Newton's constant, and C is the speed of light. To three significant figures, as I wrote there, is 3.00. Okay, so that is what the compactness of a system is. Now you can make a compact either keeping its size and increasing its mass, or by keeping its mass the same but reducing the size. And you cannot indefinitely make the system size very, very small. What happens when you do that? It becomes a black hole. You can't make it any smaller than that. It has a horizon. And for what value of R does it happen? Given a mass. Yeah, so it is 2 Gm by C square, right? That's when it becomes a black hole. So what it means is that for a black hole, the compactness is Gm by C square R divided by 2 Gm by C square R. So it's 0.5. Yeah. That's the reason why I put the tilde sign. Sign. 0.5. You can use either the ergosphere or you can use the horizon to define it. It doesn't matter. It is a loose concept that we are dealing with. And the calculations that we do are of order of magnitude. I mean, maybe it's wrong by a factor of 2, that's all. For curved black hole 2, you can define you can just take the horizon size and define the compactness, and you would get one answer. If you take the ergosphere, you get another answer. They're not vastly different unless you spin up the black hole very, very heavily. Okay? So that's the reason why I put this tilde sign saying that, if it's maximum. That's its maximum value. You can't make it any more compact than that. But typically, for something like Earth or Sun, this is much smaller than 1. As an exercise, please compute that and show that it is something like less than 1 per 1,000 or 1 per 10,000. Very, very small. And in fact, in Sun's case, it's ridiculously small. Okay? Now, why do we worry about this compactness? Where does this come from? That's what I want to motivate. It is really buried right in Einstein's equations, field equations itself. So here, as an aside, let's write down Einstein's field equations. I'd never written in such thick chalk. It's wonderful. Feels good. So Einstein's field equation on the left-hand side is the curvature, Einstein curvature tensor or Einstein tensor. On the right-hand side is the energy momentum tensor, energy momentum stress tensor. If my handwriting is not clear and if I don't say something, please do ask. It's like a class, okay? And this is the Einstein tensor. I would really like to call it curvature tensor. It really represents the curvature of space-time. What's the dimension of curvature? I'm not asking my experts here, but what's the dimension, physical dimension of curvature? 1 by meter square. Yeah, it's area, right? 1 by area. So this is 1 by area dimensionally. What about the stress tensor? What is its dimension? What is the physical dimension of the stress tensor? We said it is energy momentum stress tensor. Energy is really more like energy density, right? Or it could be pressure. They're both same. Energy density, if you wish, is kg meter square per second square divided by volume. So that is energy density. Or it also represents pressure. Pressure is force per unit area. So this is pressure and this is energy density. They both have same dimensions, as you can see. Right? It is energy momentum stress tensor, and that has dimensions of force per unit area. I would like to use force per unit area instead of energy density, because there is area here, there is 1 by area here. So I can say something about the dimensions of this. So what is the dimension of that coupling constant? On one side we have 1 by area, on the other side we have 1 by area times force. So what is the coupling constant? 1 by force, right? That's all there is to it. So 8 pi g upon c to the power of 4 has dimensions of 1 by force, or in other words, I can define what is called a geometric force GF or FG, sorry, a geometric force FG, which is made up of purely fundamental constants, c to the power of 4 upon 8 pi g. If you work that out, in physical units, this turns out to be something like 10 to the 44 newtons. Very large force. Now, Einstein's equations tell us something very fundamental. On the left-hand side, you would have heard of this on many occasions in your courses. On the left-hand side, it's curvature of space and time. And on the right-hand side, it's energy momentum tensor. Energy momentum tensor tells space-time how to curve. Space-time curvature tells matter how to move. Very famous statement. But what is important is the coupling constant. You are almost never told, I don't know if you have heard this before, that had dimensions of 1 upon force. You may have analyzed it, you may have looked at it. I don't know how many people stress it. The reason is Einstein didn't like force. So people don't want to talk about forces. But we can ignore Einstein. We can talk about forces. So I want to really think of that as that constant, as defining a fundamental force in nature. Now, after all, we experience force all the time. There's nothing wrong in talking about that. It is just that when you formulate this theory, it tells you that there is no need for a concept of some mysterious force that is acting. Classically speaking, what matter does is to alter the space-time structure. That's what it is doing. But that's okay. But when we want to compare our experiences, right, with what gravity might do, we can talk about forces. That force is extremely large. And in order to induce curvature of order unity on top of the flat space-time curvature, if this is 0 on the right-hand side, and I don't have any other boundary conditions, you of course get Minkowski space as a solution. One of the solutions of Einstein's equations is Minkowski space. Okay? But in order to produce departure in the space-time curvature G alpha beta, which I can write it as eta alpha beta plus h alpha beta, in order to make this h alpha beta non-negligible, I must have stresses in the system that can overcome that coupling constant significantly. You can't make the stresses too large either, because that will turn into black holes. That's the other problem. If you make stresses in the system very, very large, it will turn into black holes. And after that, of course, that's all that you have. You can't produce any greater curvature than that. So what we are learning is this force is important. Let's ask the question, when is this force produced in nature? What sort of systems experience the geometric force GF, or FG? I don't know why I keep calling it. And since most of our lecture is going to be about binary systems, let us consider a binary system. In this binary system, you have two masses going around each other. The size of the system is r. The speed of the system is v. It has a characteristic mass m. It could be total mass of the system. The so-called centrifugal force, or some people would like to call it as centripetal force, in the system is mv square upon the size of the system, right? This is very familiar. let's substitute for v square from Kepler's law. Kepler says v square is related to the mass of the system and the size of the system. Anyone remember what that might be? You know, he has many different forms of the law, and one form relates the velocity to the mass and size of the system. Let me recall for you. It is simply gm by r. So you can see compactness is somehow appearing there. There is no c square, but I can always put that in. Okay. Compactness first time appears already in Kepler's law. Okay, so let's substitute for v square. So this is the centrifugal force for anything that's going around in a circle. It doesn't have to be balanced by gravity. Okay, the force that is giving you, the central force that is giving the velocity does not have to be gravity. It can be electromagnetic force. But if it is gravity, we can replace this v square by gm by r. So we have g m square by r square. Now we said we want to somehow replace this back again, this m by r in terms of v square. In fact, that's what I should have done. I should have simply replaced m by r by v square upon g. And then you will get this centrifugal force, or centripetal force, Fc, equals v to the 4 upon g. Multiply and divide by c to the 4, and you get the geometric force that we introduced before multiplied by v by c to the power of 4. So compared to the geometric force, this Fg, the centrifugal force is dampened down by that factor v by c to the power of 4. As Earth goes around the sun, what is its speed? Anyone remember what that is? Earth going around sun? Is it 100,000 kilometers per second? Or 10,000 kilometers per second? Or 10 kilometers per second? Well, you know, any scale? How fast could we be going around? Okay, let's calculate that. You know, that's what you need to do. This is the order of magnitude estimate that you need to make. What is the size of the Earth's orbit? Does anyone remember what's the size or the diameter, radius? 1 AU. Good. We are somewhere now, right? Okay, what is 1 AU? This guy is spoiling the game, but still, it's okay. So it's 500. I mean, light takes about 500 seconds to come from sun to Earth, right? So it's 500 light seconds. Okay, good. So let's use that. So it's 500 light seconds. So that means its distance is something, but I'm not going to really spend time calculating the velocity of Earth going around the sun. It's of order 10 to the minus. It's 30 kilometers per second, so it is 10 to the minus 3 c. Okay? That, if you plug that back in here, I'm sorry, 10 to the minus 4. I'm sorry. Not 10 to the minus 3. It's 30 kilometers per second. Whereas the speed of light is 300,000, which is 30 into 10 to the 4 kilometers per second. So it's 10 to the minus 4. Anyway, so this is 10 to the minus 16 times the fundamental force. And so Earth really does not experience anything close to that. And so the gravity or gravitational waves that might be generated, right? Because we are talking about the so-called non-stationary part. is not so high. And sun cannot really produce very strong gravitational waves. Later on, when I look at the slides, I will show you formulas for H as well. In fact, we are going to derive that, I guess, by using these simple arguments. So this explains why the most powerful sources of gravitational waves are the ones where V is close to C. V is of order C. Or Gm by C square R is of order 1. It's only when then the source is the strongest for a given mass. Those systems which have the greatest compactness produce for you the most powerful burst of gravitational radiation. Now let's make an estimate, order of magnitude estimate. I should keep consulting my notes to see what all I want to say in this introductory lecture. So I'm going to make order of magnitude estimate of the strength of gravitational waves using the quadrupole formula. Have you heard of the quadrupole formula before? Okay, so I'm going to state what those quadrupole formulas are. In fact, last week in a summer school we just derived them, but I'm not going to repeat that whole derivation of the quadrupole formula itself. But let's start with the quadrupole formula and make some order of magnitude estimates of what the gravitational wave amplitude is going to be. So here we go. I think I'm going to continue on that side. Is it okay to continue here? You can see these things. So soon after Einstein proposed his general theory of relativity in 1915, November 26th, I believe. I always get confused whether it is 25th or 26th. I think it is 26th. He worked out that his equations are amenable to description as a wave phenomena. What I mean by that is, if you write down the metric in this form, you don't have to assume that H alpha beta is small. You simply write down this equation in this manner. You assume a certain gauge condition. And also you work with something called trace reverse tensor, but I won't bother about it because we can always choose a gauge in which the trace is 0. Then it turns out these are exact Einstein's equations. Box, which is the wave operator, operating on this metric perturbation from Minkowski space, satisfies the wave equation, where this tau alpha beta consists of T alpha beta plus terms of order h square. One can explicitly write down what that is. Okay? If you open up Landau and Lifshitz, you'll find an expression for what that is. So they satisfy wave equation. This is what he established. And he furthermore assumed that this h alpha beta is very small, in which case, in the absence of any matter stress energy tensor and neglecting order h square, this is equal to 0. That's a wave equation in vacuum, and it gives you gravitational waves freely propagating in space. Not only that, he then used this T alpha beta. He put this in. He used the conservation laws T alpha beta comma alpha equal to 0 to show that H alpha beta, which is the various components of this strain in space, are given or related to what is called the quadrupole of the system. Namely, it's simply in unit C equal to G equal to 1, but I think I have the expression including C equal to G somewhere. Just a minute. No, all through they are dimensionless. I don't know why. We can figure out the dimensions, no problem. So let's write down. It is 2 upon r q. Let's write this as hij because only space part are important. It's 2 by r q ij double dot, where qij or integral xi xj rho d cubed x, where, I mean, what is this? What are we talking about? You have a system somewhere, and there is a coordinate system that measuring distance to different points inside the source, and then rho is the energy density, or energy density at that point, and this is what is called the quadrupole tensor. Okay, and this quadrupole is what generates gravitational waves because its second derivative is the one that gives you the strain. So let me put back what the dimensional quantities are here. This has, is it g by c to the power of 4? Okay, so that's what generates these gravitational waves. And this is what I'm going to use to make order of magnitude estimates of this strain. So from now onwards, I'm going to just write h instead of different components. Let's make a guess as to what this is. We'll go back to that system of 2 stars going around each other, and we will make an estimate of what that is. Okay? From what this is, you can easily guess that this is density times volume. Therefore, this is either mass. This is mass density. This is just mass. This is xi xj. It is somehow just the size of the system. So h is of order 2g by rc to the power of 4 m r square. But then there are 2 derivatives here, q double dot. Each of those derivatives will pull, if you have a system such as, if there is a q that is going like cos omega t, each derivative will pull out a factor of omega. So the 2 derivatives will give you omega square. Okay? That's the way one can compute what the order of magnitude strain is. So if you have omega, for Kepler's law says omega square is m by r cube. Gm by r cube. So we can substitute Kepler's law back in this, and you would get 2g by c to the power of 4 to g square by c to the power of 4. You have m by small r, which is the distance to the source, multiplied by m by capital R. I can absorb 1g in this and another g in this, 1c square here, 1c square here. You would get gm by r small c square multiplied by gm by capital R c square. So you can see gravitational waves amplitudes are directly proportional to the compactness again. So this is what I call compactness of the binary. It's not the compactness of a single object, but how compact, how close they are. Okay, it is somewhat different from the original, the very first definition that I introduced, but it's still how compact this object is. Okay? But the meaning is slightly different. So again, we see directly from the quadrupole formula that gravitational wave strains for a system at a given distance are the greatest when the object is most compact. So what happens in a binary system is that you have 2 stars going around each other. They emit gravitational waves, but rather weakly. The strength is low to begin with. But that makes the system lose energy and angular momentum. The two bodies come together and they generate more waves. I'm saying all this because I want to make an estimate of the signal to noise ratios. And that's what I will motivate next, namely how to calculate the signal to noise ratios, and then we can do it for different detectors, and then I will show you how there are certain systems which will spend their lifetime in many detected bands. So this is the system we want to talk about, and its strength is proportional to that compactness. Where? Here? Oh, this one. Yeah. Right here. Yeah. This is probably, yeah. Okay, thank you. Let me write that, and 16 pi. Yeah, you're right. Are we here? Yeah, correct. So this has to be negative. Last week I was telling the students precisely that. I mean, the choice of, yeah, it's a. I mean, there are different choices. I think we used plus there, did we? What did I write for Einstein's equation? Plus 8 pi g by c to the power of 4. I guess if it is plus 8 pi g by c to the power of 4, it will be plus here, correct? Yeah. So it won't be minus, but plus. But you're right, 16 pi g by c to the power of 4. So it's the same coupling constant here too, as you can see. The coupling constant, of course, doesn't change. Yeah. Okay. What else do we want to say here? So in addition to that, we can also calculate what is the luminosity in gravitational waves. That's the gravitational wave amplitude. But the second thing is gravitational wave luminosity. And Einstein also derived the expression for gravitational wave luminosity. And that is also given in terms of the quadrupole tensor, and goes by the same name, namely quadrupole formula. And let's shift to the other board. So that's the gravitational wave strain here. And now we are going to talk about gravitational wave luminosity. Because together with these two, we will be able to calculate what the signal to noise ratio is. And in this case, it is the energy emitted by the system per unit time is what we call luminosity. It's not the apparent luminosity, but absolute luminosity of the system. And this is given by g by 5 c to the power of 4, third derivatives of the quadrupole summed over. It's a single quantity. It's just a luminosity. It's a scalar. That's all it depends on. And we can do a trick similar to the one before, namely replace q by mr square and the dots by omega, and we would get g by 5 c to the power of 4. So I have two factors of q, so it's m square r to the power of 4, and the triple dots are converted into omega, so we get omega to the 6. We can go back and use that Kepler's law here to eliminate omega square for self-gravitating systems to find that the luminosity, let's go back here, is g by 5 c to the 4 m square r to the power of 4 omega is gm by r cube omega square. So it is this. So let's simplify that a little bit. G by 5 c to the power of 4. We have m square and m cubed, so it is m to the 5. We have r to the power of 4, but there is an r to the 9. So it is r to the power of 5 in the numerator. And there is a g cube, so there is a g to the power of 4. Okay? So we're going to now absorb 5 factors of g and 10 factors of c into this. So we're going to write this as g by, no, what is it? C to the power of 5. It should have been c to the power of 5 by g. I think this is g by c to the power of 5. I'm sorry. This was wrong. Not c to the power of 4, c to the power of 5. You discover this when you see that your dimensions in the final formula is not correct. So I'm sorry. This is c to the power of 5. So the final will be c to the power of 5 divided by 5g multiplied by gm by c square r to the power of 5. So again, there is compactness coming into the picture. And it is a very steep power of compactness. We have something to the power of 5. What is the dimension, do you think, of that physical quantity c to the power of 4 upon g? Can you guess as to what dimension it must have? Just look at the remaining thing. C, what is the dimension of C, by the way? I never asked you that. Right? Does anyone know what the dimension of C is? Right in the beginning? A-dimensional, right. It has no dimensions, right? Dimensionless. Okay, so that is dimensionless. The left-hand side is luminosity. So what is the dimension of that? It's luminosity, right? And it's again a fundamental, it's made up of only fundamental constants, C and G. C to the power of 4 upon G was force. Force multiplied by velocity is luminosity. That's another way to say it. And this is stupendously large luminosity of order. You can see it is 3 into 10 to the 8 meter per second. I won't write all that. We will write it right at the end. To the power of 5 divided by 6.67 into 10 to the minus 11. That gives you 40. This gives you roughly 81 into 3. That's about 200. And this gives you another factor of 10 to the 11, giving you, Ricardo, you remember, is it 10 to the 58 erg per second? 40, 42, 42 plus 10, yeah, 53 joule per second. Of that order, okay? Extremely large number. What is sun's luminosity? How much energy does sun emit per unit time? These are the things that you guys should know at the tip of your, I think it probably comes with experience, right? I mean, so this is so luminous compared to sun's luminosity. It is about a factor of 1,000 larger than all the stars in all the galaxies in the universe. Fantastic luminosity, 100 to 1,000 times larger. Okay? Extremely large. This is equivalent to about factor of 10 to the 2 to 10 to the 3 times luminosity of the universe in EM radiation. luminosity of the universe, entire universe. Not just visible light, but all the entire electromagnetic spectrum. Stupendously large. And it is saying that it will be dampened by c to the power of 5. C was, as you saw, 10 to the minus 4 for the Earth-Sun system. So it is 10 to the minus 20 times smaller than that. Extremely tiny compared to that largest luminosity that the system can have. That's why Earth-Sun system is not a very luminous source. That's why the white dwarf, the big star, red giant, is not going to be very important. So that's the long answer. But it's after all these calculations, you can see the luminosity is going to be small, gravitational wave strain is going to be small for these kind of systems. Let me consult my notes as to what we're going to do next. So, yeah. Correct. Yeah. The way we have argued, actually it does not depend on the systems that you consider. Because as I said, it really depends on the compactness. That derivative and all those things can be for any system. It's that, so instead of omega, you would put 1 upon a typical time scale. It may be 1 upon, so omega, you're putting omega here, but replace that omega by 1 upon free fall time scale. Okay, which goes like 1 by density of the system, or square root of the density of the system. Okay, so it doesn't matter, because what we have estimated will be the maximum. Always in front of these things, there will be a asymmetry factor that you need to put in. The more asymmetric you make the system, greater will be the luminosity in gravitational waves and the amplitude. So in the case of supernova, if it is perfectly spherically symmetric collapse, it in fact won't emit any gravitational waves. But if it is rotating and collapses, it emits some gravitational waves. It is axisymmetry, it breaks the spherical symmetry, it would emit. But the best thing for us to happen is if it has some totally non-axisymmetric collapse. But we don't know, astronomers or astrophysicists rather, don't know the mechanism of collapse. And in fact, astrophysicists are not able to bounce a collapsing system so far. It collapses and that's it. It doesn't bounce back. And so we really don't understand the physics of supernova. I think that's digressing a little bit from what you asked, but that's where we are. Okay, I want to make a number of points starting from these, because I want to use the system to derive, as I said, the goal is to derive the signal to noise ratios and which systems are important in which detectors. To be able to do that, I need to make some, I will give you some proper expressions for these quantities. Namely, for a binary system, as I said, I took the example of a binary there, but they are really not, they are more generic. The arguments are more generic. So for a binary system, the luminosity is 32 by 5. Some asymmetry factor called eta square, I'll tell you what eta is, multiplied by V by C to the power of 10. It is the same formula we wrote here. It's just that Gm by R is replaced by V square. That's why it becomes V to the 10. So that's the luminosity. And gravitational wave amplitude for a binary system, just the dominant term is 4 eta m by R V square. I'm not writing the time dependence here. you can write it as simply cos omega t, but omega is a function of time. Okay, if you want, but I'm not going to use that, but it is multiplied by cos omega of t times t, but that's not a very good approximation. We write it as cos phi of t. Okay, that's the phase evolution, and I will tell you how that phase evolution comes in, but that's the additional factor. Maybe we can retain it for a minute. Yeah. For the quadrupole formula, why not? Oh, you mean if I don't write cos omega t? Yeah, no, it is there. I was just going to use the amplitude of the strength, amplitude of the strain, in order to make some estimates. Cos omega t is there always. Which one are you talking about? The luminosity is just that. It is summed over, and there is no cos omega t. Okay. The way it happens for the binary system, I don't know whether I should be really doing that or not, is you can calculate what is the energy momentum, quadrupole tensor, and you can work out the entire, it takes about 1 hour to do this calculation. One can show that that formula is what comes out. Eta, I haven't told you what it is. It's an asymmetry factor. We wrote down the picture of a binary there. It's also here. Let me make use of this. This is M1 and this is M2. That asymmetry factor eta is M1, M2 divided by M1 plus M2 whole square. Okay. This is a dimensionless number, and it tells you how asymmetric that binary is. If the two masses are equal, this is equal to 1/4. It's equal to 0 if one of them is negligible compared to the other. Okay, that's the limits. So eta goes from 0 to 1/4. It is the maximum value it can have is 1/4. So here it is gives you 2 divided by 5 multiplied by this v by c to the 10. So it tells you that when the two bodies are going around each other with 10 to the minus 4, as in the Earth-Sun system, it is going to be extremely, I have to multiply this by c to the power of 5 divided by g. So it's going to be extremely small luminosity. Okay, that we have already said. We're going to now use these two formulas to estimate how long the system is going to last. Once we know how long the system is going to last, we can use that formula then to find out what is the signal to noise ratio. That's the goal. So we can find out what that is, because if this is the rate at which the energy is lost, that is dE by dt, and where is that energy coming from? Any guesses as to what that gravitational wave luminosity, how is it generated? Is it coming from vacuum? Just generated like that out of hat? No, it can't. So where is it coming from? Binding energy of the system. So the two bodies have some binding energy. They must therefore get closer, right? They must get closer and closer. So this dE by dt is decreasing. So minus dE by dt is equal to the luminosity, gravitational wave luminosity. So you said binding energy, E. What is the binding energy of a binary? It is minus 1/2 the reduced mass multiplied by v squared. So all we have to do is to take the derivative of this. Now remembering that this velocity is not constant. It's going to change because the system is, approaching. So we are going to just use that energy balance equation right here to derive the time scale over which that system lasts. So let's do that here. So minus d by dt of half mv minus half mv square must equal 32 by 5 eta square g by c to the power of 5 by g v by c to the 10. Right. So this will give you m v dot. I'm going to now start using unit c equal to g equal to 1 so that we can reduce some writing. We can put that back later on. So it's 32 by 5 eta square v to the 9. V to the 10, I'm sorry. So let's do this one calculation properly. So this is dv by dt, but I'm going to write that as dv, capital M. This is mu. I'm sorry, it's not m, but it is mu. Mu here. So it's dv by v to the 9 equals 32 by 5 eta square by mu dt. I will write this mu, divide that by m and multiply it by m. But this mu by m is nothing but eta. So it will cancel one factor of eta. So we are going to get the equation. This is very easy to solve. It is v to the minus 9 plus 1 divided by minus 8. We have to solve it from some limits. We start from some v low or v naught to v equals some 32 by 5 eta m dt, which we start from some t naught to t. That's it. So let's solve that equation and see what that gets us for velocity, evolution of velocity. So that's v to the minus 8 by minus 8. That's the first term, plus v naught to the 8 minus 8 by minus 8 equals 32 by 5 eta m t minus t naught. So now let's do this equation. Where? Oh, here, yeah. Correct, yes, yeah. So let's how do we want to do it? Okay, we'll take this to the other side if you want. Or do I want to do that at all? Maybe not. So I'm going to write this as v to the 8. We'll take this, all the minus signs to the other side. V to the 8 equals v naught to the 8. That's all. Plus 32 by 5. No, the other way around. 5 by 256 divided by eta m t naught minus t to the power of 1 by 8. I think that's correct. Tell me if I missed something. Oh, but all that must be multiplied by 1 by 8, right? Sorry, that's not quite right. So we multiplied by 8, so that is 5 by 2. Huh? Minus 8, but I absorb that in this. Correct. Yes. Now inverted, you're right. You're right, but I'm writing deliberately in terms of that. So it is 1 by 8, right? Okay? That's what that equation becomes. So minus sign is gone. And now we take this V naught to the minus 8. Yeah, let's keep that. And this is all, okay, now I shouldn't invert it to begin with. I want to invert it because that's simple. Okay, all right. No, we don't have to do anything. Don't worry. It just comes out naturally in a minute. So now I'm going to write this as correct. So we get minus 1/8. Yeah, V naught to the minus 8 here plus 256 by 5 eta m t naught minus t. Okay, we can now take this V naught to the minus 8 as common, and that will give you V naught here into 1 plus multiplied by V naught. So that is how the velocity of the system would change. And initially at t equal to t naught, this term will go away. It is equal to V naught, so that is correct. And as time goes on, velocity keeps on increasing. And it will become extremely, it will come close to the speed of light, and one can define a time scale. Obviously, all of this must have dimensions of inverse of time, right? Because this is dimensionless, that has dimensions of time, and this must have dimensions of inverse of time, and it is called the coalescence time Tc. So it is 5 by 256, 1 by eta m, V naught to the 8. That's what I wanted. That is the time scale. And that time scale is gives you the time over which the system's velocity will increase from V naught to the speed of light, roughly. Or it becomes infinite. In this picture that I have drawn, it becomes infinite, but the system will shut off itself before it becomes even the speed of light. But the difference between becoming the speed of light and infinity is not very large, the time scale. That's why this time scale is a good time scale. So this time scale is the one that we're going to use to do the integration. But probably I'm running badly out of time. What time is it now? I promised I'm going to switch over to slides at 11. Huh? 1 hour, yeah. No, I wanted to switch over to the slides at 1 hour. So here is how the calculation proceeds. So you got this quantity here. You have the h coming from there. And you have to compute what is the signal to noise ratio for the system. I thought I'm going to do that by starting from Bayes' theorem that John introduced yesterday. But since we are running out of time, I'll quote what that number is, and then we're going to switch over to the slides. So we want to finally compute what the signal to noise ratio is, and it comes from this Bayes theorem denoting that signal to noise ratio by rho. Rho square is integral from some velocity v naught to final velocity v, or equivalently some frequency f naught. Velocity gives you corresponding frequency, to some upper cutoff frequency fu. The Fourier transform, instead of the time domain h, you take the Fourier transform, it modular square divided by SHFF integrated over. There is a factor of 4 introduced for conventions, but that's about it. So you take the inverse Fourier, you take the Fourier transform of the signal, modular square it, divided by SHFF df. If there is time, I'm going to tell you as to how one might compute in a very heuristic way, without complicated calculation, how one can get the Fourier transform for a chirp later on. But I think we better switch over to the slides and cover some of the stuff that is there in that. Correct. Yeah. This is the thing that I normally try to stress, that the maximum luminosity attained by a black hole binary is independent of what is the total mass. The luminosity is the same for all binary black holes of equal masses or a given mass ratio. And, one is troubled by what the hell is happening. How come? But it's luminosity. It's not the total energy. The total energy emitted, I'm explaining it for the sake of students, is different for different systems. Don't think that it is somehow dissipating gravitational waves or dissipating the energy of the entire universe. No. There are sources that emit more energy than a gravitational wave source. But it's just that it is a system that emits more energy per unit time than any other source that you can think of. The only exception to that is the Big Bang. Okay, the creation of the Big Bang, it's much more powerful than binary black holes. So yeah, that's a very important point. That's the reason why I derive it in terms of the velocity rather than frequency, because it very clearly brings out that there is no mass scale and there's only asymmetry in the system, that eta square, and that's it. Okay? Correct. That's the other way to look at it. There is no mass scale in the system in GR, and that means that the luminosity should not depend on the mass scale. That's correct. Absolutely. Yeah. You can. That is the maximum you can ever get. Yeah, that's right. Okay. Now we're going to use some of the things that I did. I really didn't complete everything that I wanted to say on the blackboard, but I will point out what I didn't say and how that might be obtained. And here too, I have too many slides. Let's see how much we will be able to cover. I think this we can run through pretty quickly. Can we have the slides, please? Slides? That's okay. Yeah, it's not very important. So we do want to talk about black holes across the whole gravitational wave spectrum. The idea was to use those simple calculations to demonstrate how that comes about. So we heard this already. Gravitational waves are stretching and squeezing of space-time, and I demonstrated that to you as to how, I mean, these are all going to be there for you to look at it. I derived these things from looking at those Einstein's equations, and then how the gravitational wave strain is also a compactness, and it can be expressed so, and so on. Okay, now let's move on. I gave some more arguments as to what is the maximum strain H you can have from the fact that gravitational wave is defined in the so-called wave zone, which means that the distance at which you are looking at is greater than the wavelength of gravitational waves, which itself is much, much greater than the size of the system, which implies, looking at this formula here, that H is always less than 1 in the wave zone. But it is not much, much less than 1. I have just indicated that H is less than 1. It is the same formula we wrote down somewhere there, except that I have rearranged it. Instead of small r, I have used capital D here. That's all. And it shows that it can be less than 1, but not much, much less than 1. So we can't neglect the right-hand side of the Einstein equation where I wrote down order h square terms. They cannot be neglected. They are the ones that generate the so-called post-Newtonian expansion. So in summary, then, binary black holes, the waveform is characterized by a very slow, what we would like to call adiabatic in spiral, because the energy is conserved at each order in the post-Newtonian expansion. But it is followed by a fast and luminous merger, and that is shown in this graphic here. You can see the frequency is very slowly evolving in the beginning, but it evolves very rapidly at the end, followed by a merger phase, which can only be modeled by numerical relativity simulations currently, but there is effort to model them by using, I wouldn't say perturbation theory, but more proper understanding of numerical relativity simulations, followed by ring down. That's the character, but this, as we heard yesterday, is characterized by a large number of parameters: mass ratio of the system, large black hole spins, misaligned with the orbit, eccentricity, etc., can determine what exactly the shape of the system. So it means that we have to look for many, many different waveforms, but that also means that we can gather all this information by properly analyzing it. So waveform shape in general tells us about the component masses, the spins and eccentricity, the intrinsic properties of the system, whereas the waveform amplitude in a detector or a detector network can tell us about the source's position on the sky, how it is oriented with respect to the detector and its distance. That's what the waveform amplitude can tell us. So this is the size of that amplitude. So that's how we gather. But that is not the full story, because if a system lasts long, then the waveform phase will change due to relative motion of the detector and the source. And that modulation then will also help us gather information about the sky position and other quantities. So this is really, for what I'm saying in this slide, is strictly true only for systems that last for less than half an hour in a detector band. If it lasts longer, then other effects are important. So I want to walk you through this space of mass and frequency. Mass on the x-axis, these are masses of binary systems in solar masses, and that's the frequency in hertz. As you will notice, it covers 12 orders of magnitude from 1 solar mass to 12 solar masses, 10 to the 12 solar masses, sorry. And similar 12 orders of magnitude in frequency, 10 to the minus 9 hertz, which would correspond to something like 30 years. That's the period of gravitational waves there, to 10 to the 4 hertz. That's 10 kilohertz frequency. So it's a wide frequency range, and there are detectors that we will talk about in a little bit that will target different frequency ranges. At the high frequency end, from about 1 hertz to 10 kilohertz, are ground-based detectors. So I call it ground here. In the frequency region, about 100 microhertz, microhertz, maybe a little less, all the way up to 1 hertz, is targeted by the space-based gravitational wave detectors such as LISA. And we are going to look at the synergy between these two in a minute. At very low frequencies, wavelengths of the size of the galaxy or many hundreds of or tens of light years. I can't call it size of the galaxy, but what I mean by that is it is really not the solar system scale, but much bigger scale, something like of order a parsec. Would it be even a parsec? No, probably not. Not even parsec. It's 10 light years scale is the frequency targeted by the pulsar timing arrays. On this, one can draw what is called the last stable orbit frequency. That's the line that denotes that. I talked about the upper frequency cutoff in this integral here. That upper frequency cannot be infinite because these two bodies are not point particles, they are solid spheres, and when the two black holes begin to plunge towards each other, you basically end the signal. More precisely, you end the signal when the two black holes collide with each other, a common horizon forms, and that settles down into quiescent curve state. I'll show those curves as well, but this particular curve corresponds to what is called the last stable orbit. After that, there are no more stable orbits. Okay, the two black holes are going around each other, and that is given by an equation which is F. The frequency is inversely proportional to mass, and that is that line. Okay, once a source, let's say a 100 solar mass source, is evolving along this line, it reaches that point. After that, it cannot sustain itself in an orbit. That's the meaning of that. Above that line is what is called the 2-2 quasi-normal mode frequency. So the two black holes come and merge, plunge towards each other and merge, and initially they are highly deformed, and that deformation they get rid of by slowly oscillating and settling down to a quiescent Kerr state. The quadrupole mode, the so-called 2-2 quasi-normal mode frequency, is given by that line that's also inversely proportional to mass. So larger masses means smaller frequencies, and that's given by that. You can see it's parallel to that curve, right? But there are other modes as well. It's not just the quadrupole. There is octupole, sextupole, and so on. I draw here the octupole mode, 3-3 quasi-normal mode frequency. That would be there, and we have no radiation beyond a certain region. The 4-4 quasi-normal mode is hugging that gray region. Numerical relativity simulations tell us that for equal mass binary black holes, or roughly equal mass binary black holes, there is no significant radiation. That is not any more than about 5% in modes more than about 4-4. The frequency, as I said, keeps on increasing up. If you look at 5-5, it's already about 1% or 2%, unless you make the system a lot of spin and high energy. So, you can put another line somewhere there, but above that, there's no radiation expected. So, yeah, those also have frequencies in between those two. The lesser so typically speaking, L equal to M has the largest frequency. L less than M, M less than L, will have lower frequencies. 4-2 has frequency very similar to 2-2. Or 8-2 will have frequency very similar to 2-2. Although not all the time. I mean, is that something you have studied, Ricardo, at some point? Any frequency, correct. Yeah. Yeah, a factor of 2. But remember, this is a log-log scale. Okay? So it won't really, it'll, yeah, okay, you can have, the opportunity to put something here. The point about this slide is that if you see anything in that region above those lines, significantly above those lines, that is an indication of one of two things. Either general relativity, there is something wrong, its predictions, something wrong, or that the systems that we are observing are not black holes. That is what that would indicate. They are not black holes. They could be some other exotic objects like boson stars or soliton condensates or whatever. We don't know boson condensates or soliton stars. We don't know what they could be, but that is a way to test. So here is a way to test whether we are seeing some exotic object. I also plot on this line on this slide a dotted line that shows you starting from which the system would last for only 1 minute. So let's consider a 100 solar mass system. If it starts at that frequency there, then it would last for only about a minute before merging. I will also show you on this slide, okay, so this is a 1 solar mass black hole, a binary that would last for 1 minute starting at something like 30 or 40 hertz. This is 1 day to merge, and that is 3 years to merge. You can see these are all different, they are the same scale, but there are different different dependence, different slope on mass compared to that. So they intersect these lines here. After some time, there's no time to merge at all. If you start from somewhere, let's say here or there, the system immediately merges in those frequencies. That means that this lower frequency cutoff here, F0, and the upper frequency cutoff is the same. Therefore, you don't see those systems in those detectors. So let's look at this example. Here, this system, I want to, take this 1 day to merge. 1 day to merge is this line here. So a 10 to the 2 solar mass black hole would take something like 1 day to merge starting at that frequency. But starting at this frequency, it would take 3 years to merge. And this is what I think Ricardo wanted me to talk about. Namely, there are systems that would appear in, let's say, this band here. This is what? A few times 10 to the 4 solar masses. But that will never appear in the ground-based window, because ground-based window, that is the absolute limit, 1 hertz. So you will not be able to observe sources greater than 10 to the 4 solar masses in ground-based detectors. That's the maximum limit. 1 hertz is a frequency that is very difficult to achieve. However, 10 hertz might be more realistic. So if you put that limit there, that's about few hundred solar masses. So that is the limit that is set by fundamental physics. Okay? No matter what you do with those frequency, with those detectors, the sensitivity, strain sensitivity, is not going to help you. Okay, yeah. It is just that these two systems have are going to merge. So this here, 10 to the 4 solar mass black hole, are so large that their frequency will never be as large as required by ground-based detectors. Yeah.
What is the limitation of the ground-based detectors?
Oh, it is about 1 hertz. Why 1 hertz? Yeah. This is limited by the so-called gravity gradient noise. So let me explain this. Please ask this question when I show you some sensitivity curves, because I'll show you what those sensitivity curves are and where the limitations come from. Okay. So a system like a pair of 10 to the 6 solar mass black holes will take only 1 day to merge starting at that frequency, but it could last for about 3 years starting at this frequency, which is still in the LISA band. So going on about here, this system here, which is a few, or 10 to the 11 solar mass binary black hole in the pulsar timing array, will never merge. Because you can see it's about 3 years here. If you draw another line somewhere there, it is going to be something like 30 years. within a year it's not going to merge. It takes many, many years. And in that 30 years, you will probably see one gravitational wave cycle. So that's what that tells us. Going on, I will draw another set of curves now. This blue curve indicates the line starting from which its frequency will change by 1 upon the duration that I mentioned. Okay? So here, the frequency is going to change by 1 bin, more than 1 bin. That means it's going to take 1 day to chirp up in frequency. Let's put 2 more lines. This will take 1 year to chirp up. This will take 30 years to chirp. What it means is, chirping means the frequency changes during the observation. I did not quite have time to derive that here. Namely, if you look at this velocity here, it depends on a certain combination of the masses. There is also V0 to the power of 8. It will make that whole quantity what is called a chirp mass of the system. Therefore, by measuring this V or V dot, in fact, more precisely V dot, where's the expression for V dot? Yeah, V dot is here. V dot is 1 upon V to the 9. It depends on a certain combination of the masses. We can measure that only if we can measure V dot or F dot. So that is what these lines are. If a system starts on this line, then I can measure its masses and other parameters. If it starts below that line, I can't measure it because it takes too long to chirp up. Above that line, no problem. So in that sense, a system like this will never chirp up in the pulsar timing array band, which means that we can't really get the masses of the system. Only if it is above that line, it will chirp up in 30 years. Otherwise, we can't observe it chirping. So change in frequency in this region is less than 1 nanohertz. Okay, it will just sit in one frequency bin for 30 years and don't change. Whereas on ground-based detectors, you can see I did not draw any line hugging or touching the ground-based detectors. Ground-based detectors will always observe chirping systems within a day. Typically, it's within a few seconds. The system will chirp up. So this diagram is called the mass frequency diagram and contains quite a lot of information that you can learn. I mean, I probably, it's a good summary. And what this shows you is the luminosity in gravitational waves. It increases rapidly as V by C to the power of 10 or F to the power of 10 by 3, frequency to the power of 10 by 3. And as a system chirps up, its luminosity is increasing massively. It increases by 6 orders of magnitude when its velocity increases by just a factor of 4. It's 4 to the power of 10 or 2 to the 20, which is a million. Okay, so frequency is changing, not frequency. Velocity is changing by a factor of 4 will increase the luminosity by a factor of a million. So I think I'm going to skip that. Somebody talking about EMRIs? You are talking about, or somebody else? Okay, yeah, I'll skip those. I think I'm going to skip this too because I did not have time to. I thought I'm going to talk about certain things, but I didn't. Let's now go to observing these sources. So we talked about the binary black hole sources. How are we going to observe? Pulsar timing arrays, I don't think you asked me to talk about, so I'm going to skip. Okay. Then I should probably skip those bunch of slides that I put together. I can give you an overview. Okay, sure. Let's go back. Okay. So pulsar timing arrays, the way they monitor the sky, gravitational wave sky, is not very different from the way interferometers. All we are doing is to look at the Doppler modulation in electromagnetic signals caused by passing gravitational waves. Okay, we can think of it as tidal effect of gravitational waves, Doppler modulation or frequency modulation of these. They're both same. So pulsars are very good clocks. They're not the most precise anymore. Atomic clocks are really taken over pulsars nowadays, but they're still very good, and they are out there in space where we want them to be. Just like the GPS is able to monitor the timekeeping here on Earth and therefore tell us what the positions of various objects on Earth are, pulsar can tell us that. I mean, interstellar travel can be very easily accomplished by using pulsars, but on top of that, they also, because of their precise timekeeping, detect gravitational waves. And there are now worldwide many different collaborations that have formed which monitor. If you monitor just one pulsar, you can't tell whether there is a gravitational wave. You are looking at the ticks of a clock, a pulsar, but it is not a very precise clock. There are internal disturbances that can change the ticking, and so it's not a passing gravitational wave that is changing the ticking of the pulsars, but something else. So one needs more than one pulsar, and typically about half a dozen. Pulsar timing arrays are going to use just 2 good pulsars to make first detections. That's the hope. But in order to have a good detector network, probably you need about half a dozen of them with very good timing accuracy. So people are starting to form these collaborations, and here are some examples. European Pulsar Timing Array has put together data from their own detectors. Parkes Pulsar Timing Array is the Australian one. North American Nanohertz Gravitational Wave Observatory, as well as the Pulsar Timing Array, have received the greatest amount of money to look for gravitational waves from in nanohertz region. And finally, International Pulsar Timing Array. I don't know what the situation is. Maybe Stephen Taylor is going to tell us what the current situation about those is. But far in the future, this is the international project. Here is an artist's conception of how a square kilometer array might look like. This is now completely outdated because of this, the split of the SKA between 2 different continents. Anyway, the pulsar frequency. We draw now a bunch of sensitivity curves. So we'll see exactly the same curves, something like 20 different curves, strain sensitivity and source strength, all in this strange unit called meter per root hertz. You saw square there, and that quantity there, SHFF, is what we are going to plot, but also square root. So we're going to plot square root of that. We're going to plot the square root of that. So that is the signal strength. And then we're going to show both of them on the same curve. Okay. So this is the European Pulsar Timing Array sensitivity curve. So it has a very sharp rise at a certain frequency, because you don't have data accumulated over time scale larger than that. That is the low frequency limit. And then it raises by some power law here. And they have used 5 pulsars at 100 nanosecond timing, with 100 nanosecond timing residual, timed every 2 weeks for about 10 years. That's what the capability of this network is. This is the one for the others, PPTA and nanograv, are not very different. This is the typical sensitivity that they have. In order to search for gravitational waves, they estimate this has to be at the level of 10 nanoseconds. But at the moment, they have 100 nanosecond. IPTA will use 20 pulsars at 100 nanosecond timing residual, timed every 2 weeks for 15 years. And finally, SKA hopefully will discover 50 pulsars at 30 nanosecond timing residual, timed every 2 weeks for 20 years, which means this is how long you can observe. So that is really determined by that 20 years. This line is nothing but 10 to the minus 9, which is 20 years. That's all. You can't observe wavelengths that are, what is it? Yeah, 1 oscillation. This is less than 1 oscillation frequency. That's all. Yeah, it's limited by how long. That's the reason why it's very sharp cutoff. And their primary motivation is to observe stochastic background created by binary black holes. although they can actually observe binary black holes, I think in the case of SKA at redshift of 0.1, their primary goal is to observe not a single black hole, but a stochastic background created by a population of binary black holes. They can detect omega of 10 to the minus 8 after 5-year integration in EPTA. I have put the final limit here, 10 to the minus 14 in omega after 20 years. So we are talking about, no, SK has not started, by the way. So we are talking about at least 20, 25 years to reach that level, but unfortunately that is still not enough to detect omega from inflation, but it may be good enough to observe binary black holes. I think it's more like here that we will begin to observe something, 10 to the minus 11. I think that's what the pulsar timing array community hopes to achieve soon. Okay, what's the current, what do we know currently? So this is the strain, sorry, that's the strain left by, what I meant to say was, that's the strain left by a supermassive binary black hole. I think this is where, no, that's the current limit, I'm sorry, that's the current upper limit. No gravitational waves have been detected by pulsar timing arrays so far, but they have been able to set these upper limits. And the best upper limit so far that we know is an omega of 1.6 times 10 to the minus 9 at 2.8 nanohertz. That's the best upper limit. There are, these are the references, those are the nanograv upper limits, and so on. Okay. Moving on, next is LISA. LISA is a large class mission in ESA's Cosmic Horizon program, and just less than a month ago we heard that it has been accepted. The proposal to host this in space by 2034 has been accepted. It consists of 3 spacecraft, 1, 2, and 3, in heliocentric orbit. The last I heard, they don't want to have 2 daughter boards and 1 motherboard, as shown in this diagram, but rather 3 equivalent spacecraft, correct? That's what it would be. I stole this diagram from ELISA, which consisted of only 1 million kilometers and a mother and 2 daughters, which means it had only 1 interferometer. Whereas if you close the loop here, you can get 3 interferometers, or 2 equivalent L-shaped interferometers. Yeah, the current arm will have 3 arms, all 3, or 6 slings that Massimo was talking about yesterday. And these go around the sun, so it's in heliocentric orbit. It's not earthbound, it's sun-bound. And so, what did I want to say? Not only is this going around the sun, but as you can see, it is a cartwheel. The orientation of the system, very naturally, because of celestial mechanics, goes through a cartwheel orbit, and as a result, it induces additional modulation in the signal that will allow us to break some degeneracies. 150 million kilometers, okay. All right, so this is the, again, the frequency, yeah. Yes, if all 3 will come back, all 3 arms come back, then we can measure the polarization. Otherwise, it will be very hard. I don't know whether it can be measured at all. The modulation should still allow, right, Massimo? If you have a 1-year source, because it sees different parts of the system, it should still be possible. Yeah, location, but yeah, long-lasting sources. It should be possible even with ELISA, but it's not ELISA anymore. Don't call it ELISA. Call it LISA from now onwards. Yeah. No, you measure more. As I said, if you have 3 V-shaped detectors, so you have 1 V like this, another V like this, and a third V like this, then you measure different combinations of the polarizations, H plus and H cross. Oh, that is different. Oh, you mean GR test. GR test cannot be performed with LISA. No, that's correct. Oh, but if it is modulated, so you see, this is at one instance, okay? But if you go around, then you are actually sensitive to different polarizations at different times. So in the case of LISA, no, no, no. In the case of LISA, it will last for 1 year. Okay, so maybe 3 years. I mean, I showed you in the previous graph, 10 to the 6, 10 to the 6 solar mass black holes can last for even 3 years. We just have to get lucky that the system just starts at that point when we begin to observe, but typically 1 year. Now, so GR polarization, this is an open problem. You know, one of you guys should take this and actually work on it. Namely, how good is LISA in extracting the non-GR polarizations? I thought I will actually. Yeah. Yes. But you haven't. Yeah. Yeah. I think it'll be good to. Nobody has looked at this. Yeah. Yeah. No, but only 6 independent. We'll get 6. Oh, you mean in theory? In theory, there are 6. Yes. Yes. Correct. 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 Yes. No, but then it is modulated, right? Because of the modulation, you can get the position of the source. You still get 5, but I think breathing mode is definitely doable with. Correct. It's only to get a signature. Even if the other modes are present, it will not be consistent with H plus H cross. I think it's a problem worth exploring. By the way, I was writing this NASA proposal, and I thought, let me put this as a problem. But I could not do, I want to always do a back of the envelope calculation too. I could not complete it, so I did not put that as a proposal in the end. Correct. No, because they move and they cause modulation. That is precisely what I was trying to impress upon you. But I think Ricardo explained that these are position dependent, right? The antenna pattern function depends for the different polarizations, has different dependencies on theta phi. That's what he's pointing out. Oh, what are we doing with time? What time is it? You know that. You have a model. You have a model. You have a model for the source. I think we should do that. Let's come back and do it. Because I think it would be a nice problem for a PhD student or a postdoc to look at this. I really thought this would be a nice proposal, but didn't have time. Anyway, shall I go forward? Okay. Thank you for the question. So this is a similar curve to what you saw before, namely frequency and sensitivity and source strength, except now it is LISA sensitivity. Same units. Okay, so let's walk through. This is the classic LISA here in black. That's the 5 million kilometers. E-LISA is this 1 million kilometers. And the LISA of today, and I didn't have time to do that. I just got the curves about a week ago, and I have been remaking these figures. But I didn't have time to put on this plot. But the signal strengths would be correct. The LISA curve currently is in between these two. And it staggers between these two, in fact. Exactly staggers. With a speed spot slightly to the right and to the left of those two curves. Yeah. Those oscillations happen because the so-called long wavelength approximation, in which the wavelength is much larger compared to LISA, is not valid here anymore. And you lose sensitivity at those frequencies because the two spacecraft have come back to their equilibrium positions before the light return. Is that a good way of saying it? Yeah, yeah. This is called the free spectral range in the context of LIGO detectors. We do have sensitivity there. We don't do a good job of detecting things at very high frequencies in LIGO. I don't know why. 32 kilo. We don't sample it first of all, right? I mean, do we have the full 100 kilohertz samples? Okay. Okay. So what Chris is saying is, in the case of LIGO, we have a similar problem at very high frequency. We don't analyze data there because it's difficult to calibrate. 30 kilohertz is a very fast time scale. People can't calibrate at very low frequencies. They can't calibrate at very high frequency. We do what we can. So it's not analyzed in the case of LIGO. It's a different frequency band, of course, but it's not analyzed in the case of LIGO. In the case of LISA, this is a thing that I have not understood so far. I've talked to Carsten Dansman many times. Apparently, calibration is not a problem. Can you explain that, Massimo? Is that something that you understand? Why calibration is not a problem in the case of LISA? It's the amplitude in the phase of the data that we are getting is somehow, it's not a problem. Every time that's what he tells me, and I'm supposed to believe it, but I don't know how. He explained to me once, but I didn't understand. Correct. So what we do in the case of LIGO, to explain to students, is we push the mirrors. We apply a force. It could be an electrostatic force or force from a photon. And we think, or we can measure what the applied force is. And then we also know how the detector responded to that force. So we can measure the phase and the amplitude of the recovered signal, and we know what was the applied signal, and we can calibrate. And we can only calibrate to something like few radians, few degrees, 3 or 4 degrees in phase, and about 5% or a few percent in amplitude. Now, that's what I mean, that. Yeah. But somehow he says it's not a problem. In the case of LIGO, the problem is that the responses are measured inaccurately, and the applied forces are not very well known. And those are the uncertainties that play havoc in knowing what the response is. Right. Yeah. Yeah. I think I'm going to ask Carsten to actually address that issue in one of the meetings. I mean, he and I are going to the same meeting in the next couple of weeks. Yeah, no, he should give a talk on why this is not a problem, because this is absolutely critical for all the tests of GR, everything we are talking about, and he needs to convince us basically that it can be done. Except the distance. We don't know how far they are exactly. I mean, Lisa. How well do we know the distance, though? Normally, astronomy doesn't measure distances very well. That's what I mean. That okay. This may be. I asked him whether, oh, is it because of the calibrating sources? He said no. LISA can self-calibrate. That's the answer. He once explained to me, but you know,
Calibration might be in which it takes this T channel, which there is, we know there is no signal,
mm-hmm.
and then you can have a good assessment of the noise level. That
Right.
is very much like you do in astronomy.
Mm-hmm.
All
He could have used null stream as an example. I would have understood, but he never used that term.
didn't do it.
No, he said something else. But I will ask him again. But this is an important problem as well. You know, students interested in this could work on the limitation of LISA due to its calibration uncertainty. People have made career out of just writing one paper on that topic for the ground-based detectors. I know. So it's important to you can see how important some of these topics could be. Okay, so those are the two noise curves. These are known systems. So here are the calibration sources that Massimo mentioned. These are the systems that we know exist out there in the sky, and they're given names, strange names such as RxJ806 or V407 VUL. They're all what are called AMCVN systems. And these cataclysmic variables are binary systems with known gravitational wave amplitudes and frequencies, and therefore they appear in the plot wherever they are. And some of them will be observed, and we can calibrate the sources, calibrate LISA. No, they are. These are white dwarfs accreting, isn't it? Accreting white dwarf systems, interacting systems, and I wanted to say something. Yeah, the fastest known system, the most luminous known system before LIGO discoveries was one of those. It had how many minutes? 11 minutes orbit or something like that. And it was the most luminous gravitational wave source known, and that's what we pointed out in our article. You know, Bonanno, myself wrote an article. We pointed that out. So it's one of these systems. These are double white dwarfs. These are also known, and this particular one will be certainly detected in the new LISA as well as in classic LISA. The way this is, these dots are written, if they are above the noise curve, then you detect them. So in this, just widely, just about barely detected, because I have taken into account the signal to noise ratio that is required in order to detect them. So that's how I place those sources. These are ultra compact X-ray binaries. They're also known from astrophysical systems, and they appear there. This is a picture of the white dwarf, by the way, two white dwarfs going around. It was actually first time made for a white dwarf system. Okay, go on. This is stochastic background of omega equal to 10 to the minus 9. It could be binary supermassive black holes or primordial black holes. It would produce that. Next up is supermassive black holes of various kinds. I have drawn, for some strange reason, only equal mass binary black holes at a redshift of z equal to 1 for these cases, z equal to 20 for 10 to the 4 solar mass black holes. So you can see LISA can see binary black holes to the edge of the universe. A 10 solar mass black hole would also have a curve like this, but it has to be much closer, something like 20 megaparsec or 30 megaparsec. But it will continue. It will just go on and on and on, and it will appear somewhere there in the ground-based detectors, right? Merge somewhere there. This is 10 to the 0. They would merge at 1 kilohertz. And there are special sources which I passed very briefly. They are called extreme mass ratio in spirals. These are small black holes in spherical orbit around a big black hole. They would produce signals like this, because it's not just a single harmonic. You saw some slides from talk yesterday where they are in zoom whirl orbit, and they would produce tracks like this, the 10 harmonic shown, and they would be really spectacular sources in the case of LISA. So that's the summary of all the sources. Ground-based detectors, we know where the detectors are: Livingston, Hanford, Virgo, Geo, LIGO India and Kagra. And this is in this strange Mathematica map where the detectors are. They are separated by 10 milliseconds, Hanford and Livingston. If you add Virgo, the baseline increases to 25 milliseconds. And then if you add Kagra, it increases to about 30. But it is LIGO India which actually not only increases the baseline to about 40 milliseconds almost, but it breaks the degeneracy because it's in a different plane. These 4 detectors are roughly in a single plane, whereas they are in the northern hemisphere like this, whereas LIGO India is somewhere here, and therefore it's in a different plane, and that breaks certain degeneracies in our measurement of parameters. Detector in South America will absolutely break even more. I agree with that. Yeah. Yeah, but unfortunately, at the moment we don't have, but hopefully there'll be one more. So these gravitational wave detectors are wonderful. They can see something like 40% of the sky at any one time, a single detector, but not all of the sky. So, and that is represented by what is called the antenna pattern function, which is how the sensitivity varies as a function of the sky. What I'm plotting here is what is called the amplitude amplitude pattern function, which is the average for both polarizations, only H plus and H cross. So it is F plus, for people experts, it's square root of F plus square plus F cross square. So for the Hanford detector, it would look like this. You can see if the sources are just above the head or below the feet, they would have the best sensitivity. But the detector can have null direction. So if you have an L and gravitational wave is coming in the direction bisecting the 2 detectors in the plane of the detector, then it does not have any sensitivity at all. And there are 4 such directions in which that can happen. If you add one more detector, some of the holes get filled. So there's a Hanford and Livingston. They're almost same, oriented in the same manner, so they don't really fill the entire sky. But if you bring in Virgo, then you have no more any hole left in the sky, although it's anisotropic sensitivity. But with something like 5 detectors, you have almost isotropic sensitivity all over the sky. So we can integrate and build signal to noise ratios coherently, tracking signals in phase, but it also allows us in software to say where the signal is coming from. Although it is isotropic sensitivity, we can tell where the signals are coming from because of the modulation that they induce. The different, not in the case of ground-based detectors. In the case of ground-based detectors, there is different arrival times of of a single frequency. They arrive at different times and different detectors, and that's how we can tell where in the sky the source is located. For in the future, we have plans to build Einstein telescope, which I won't talk too much about. So this is the sensitivity of initial LIGO, which did not detect anything. That's advanced Virgo and advanced LIGO. Those are the strain sensitivities. And finally, the Einstein telescope, which is a future detector, which will have an order of magnitude better sensitivity than the other 2. Incidentally, you asked a question about what is the limitation in observing sources below that frequency. In all these cases, it is so-called the gravity gradient noise. Namely, at these frequencies, the fact that a piece of earth close to the detector moves because of density waves on the earth will cause gravity gradient noise in our mirrors. If you take a mass and oscillate it close to the mirror, it will induce noise. Okay, that's what this is. But due to the change in density of air, density of earth, due to passing seismic waves, but if you go underground, you can mitigate them. Yeah. Even clouds, falling leaves, or density change in the density of air, all these things cause problems. So they are the ones that limit the sensitivity. If you go underground, you can see that wall gets shifted. You should not think, oh, improve the sensitivity infinitely. That's not the way to think about it. We just move the wall to the left by going underground. If you go something like 100 meters down, already most of these sources vanish, and you can push from something like 10 hertz to about few hertz. I think, if the 2-3 hertz is what would be the limitation here. Now let's put some sources on top of that. So this is a binary black hole at 250 megaparsec. That was 10 solar mass black hole. It is similar to the second observation that we made, which had total of 22 solar masses. And that was at something like 450 megaparsec. So it would be somewhere here. It couldn't have been detected by initial LIGO. It was detected by advanced LIGO, but it left a trace something like this. Okay, something similar to that, but at slightly earlier frequencies. Not quite 500 hertz, but more like, yeah, we don't know exactly where because we didn't see the ring down part. That would be binary black hole at z equal to 5. So Einstein telescope would detect systems at that distance. So anyway, those are numbers. We don't have to look at them. These are binary neutron stars, but we are not talking about binary neutron stars. So let me skip those. Those are binary neutron star black holes at 1 gigaparsec and so on. I think I don't know why I included all this. No. To compare, the stochastic backgrounds at best in our Einstein telescope might be 10 to the minus 11 or 10 to the minus 12, just to compare what we were doing. Okay, that's the capacity of these detectors. And now people are talking about not just Einstein telescope, but also going beyond. The CE stands for Cosmic Explorer. These are not projects. I have time scales here. They are more where we want to be, but not where we will be. I already know that, for instance, Voyager, 2025 might be okay for Voyager. But I know that Einstein telescope cannot be 2030. It's too, already we are past that kind of time scale. Cosmic Explorer 2035 may be possible. So what will they achieve? This is a paper that we put out a few months ago for reference. Sorry. No, 2030 sounds too early to me. It may be more like 2032, 2034, but it keeps on pushing, as we delay, as we are delayed by the funding agency. So far, there is no proposal for these objects. That's why I call them, they're not projects. They are not funded in any sense of the word. None of them are funded, except Advanced LIGO. These are not funded. Okay, they are just plans in our head. So this is a more concrete Cosmic Explorer, what I called CE in the previous slide. That's what this sensitivity curve is. And I'm going to use that to make some estimate of how far we can see those sources. So as a function of total mass, this is the redshift up to which we can measure. Forget about this SenseMon. This slide was made in the context of some LIGO Virgo. So forget about that. So this is advanced LIGO. This is where we are. We know definitely we can see these sources. When advanced LIGO begins to operate at its design goal, we will be able to observe sources up to redshift of something like 1 on average. But in order to observe sources to the edge of the universe, you only need to make about an order of magnitude in sensitivity. Already Einstein telescope can see sources at redshift of 10, binary black hole sources. But we don't know whether these sources exist at such distances. Cosmic Explorer, on the other hand, can see up to redshift of 50. But there is an advantage to having those more sensitive detectors. Not only can they see to greater distances, but for sources nearby, they can have greater signal to noise ratio. So here is the volume that is covered, gigaparsec cube per year. So this is the volume times time for advanced detectors. as you can see, these as a function of redshift, how the volume covered increases as a function of mass. These are for Voyager kind of detectors, whereas for Cosmic Explorer, even for binary neutron stars, you cover a significant volume of the universe coming in from them. You can talk about other kind of things. These two sources were visible for only 200 millisecond and 1 second in the first observing run, whereas those very sources will be observable for 25 seconds and 600 seconds respectively in Einstein Telescope or Cosmic Explorer. They had 10 to 50 cycles in O1, whereas they will have 200 to 1000 cycles. Why are they important? Because they will allow us to measure, to do tests of generativity. Here are some other numbers that you can look at. How much time do I have? -1. Okay. So this is sensitivity of LISA for supermassive black holes, but it can have sensitivity even lower. Let me show you one slide that demonstrates Einstein Telescope here and massive binaries here. So there is a synergy. This is already a redshift of 0.5 in the E-LISA detector, but there is synergy in observing sources in both the ground and space detectors. Yeah. So I can continue from the here and then talk about rates at that. So let me leave it at that, and thank you.